Not in super great shape, so I'd like to keep it short today. We can do some more next time. So
That'd be great. Yeah.
yeah, a half an hour or 45 minutes is more than enough for me. Um, Hello, everybody. Good to see you.
Yeah.
And so what would you like to talk about from last time, or you have any questions or comments?
I have a very basic one, and that is installation of 3.66.
Yeah, there's no installer. It's pretty easy. You just
Yeah, except I
unzip it.
failed. Yeah. I want to know you said that keep the DLL in the same place as executable, but you said there's one Kepler file. Well, there's two Kepler files. And
Why
so it
don't
doesn't
you?
want to identify, it doesn't want to find the catalog.
Yeah. So something must have happened in the Google Drive upload because the file seems to have originally got split into two pieces. Very
Yeah.
weird. Like half of the files are in one folder, and then the other half are in another folder, and that kind of doesn't work. So what I asked you to do is to re-download the catalog. Did you do that, Pat?
No, I didn't. I'll be sure I still have, yeah, I have the link. Yeah. Yeah. Okay. I'll re-download it. Okay.
Right. So Leon pointed it out, and Scott, I think, pointed it out, and several other people couldn't use it either. So,
Okay.
And the strange thing is it went up okay because it's been up like that for years. I don't know what actually maybe in the middle of the night, I was sleepwalking and hit the wrong button or something. I don't know.
Okay.
Anyway, so it should be very simple. If you download the catalog, let me share my screen.
Yeah, let's see if I don't think I enabled it. Okay, there you go.
I don't even know if I have to. It's really, if you have the link, and if you don't have the link, I'll send it out to everybody on the email list. If you have the current link, you should get the complete catalog. It worked for Scott, for Leon, and for several other people. So it seems to be repaired because I re-uploaded it.
Okay, maybe I have an older download. Maybe that may be the problem.
Okay.
Well, you're seeing the same, Pat. You're seeing the same problem everybody else saw. And I think Dave's fixed it. So.
Okay.
Right. So you should be able to navigate to a folder called Kepler. Just select that folder, and it should find all of the. It looks to see if all of the right stuff is there.
Okay. All right. Well, since this is a well-established solution, I don't want to take up the time. So that's my first question.
Good question. Anybody else?
I'll always fill any available space with questions. I don't want to take up too much time either. Okay, but I guess, so I was trying to articulate the kind of the overarching theme in my mind. I'm thinking about doing some curriculum around this with my, well, it would be with my beginning class, so it would have to be sort of big picture stuff in the coming weeks. And so I just want to make sure I have kind of the big picture correct, basically. The main idea here is that in order to see very small movements of stars, you need an extremely accurate plate solution. And plate solutions, like from astrometry.net or elsewhere, sometimes like they're fine if you're looking for sort of larger movements, but in order to do like a plate solution of the accuracy that would be needed for these very small motions, you have to take into account first of all, many sources of noise, and I wrote down what those were at a previous meeting, but also like which stars you're using as benchmarks. I don't know what astrometry.net uses, but my impression is you're using Gaia DR2 positions, but you're playing those forward according to the proper motions that were measured there, and accounting carefully for the error on both the positions and the proper motions from Gaia DR2, and sources of noise in the image, and like weighting things based on whether the stars are close to the edge of the field and where they are in that saran wrap thing that's typically, and so by means of very careful consideration of all these factors, and let me know if I left out a major one, then you can get an accurate enough plate solution so that over time, very small motions of stars will rise above the error. And will be able to be detected in a way that they wouldn't with kind of less careful plate solutions. Am I on the right track?
Absolutely. So you brought up, I think, pretty much all of the major points and problems and issues. Plate solve programs like astrometry.net and Bob Denny's, whatever he calls it, I can't remember, and so forth, their purpose in life is to tell you where you're pointing with as much accuracy as they can. So, you know, they use these various catalogs and so forth. And I have too. I originally used the Hubble GuideStar catalog, which was kind of full of errors and holes and so forth, but it was good. I mean, and then I used UCAC3 and then UCAC4, which is what you've got right now in your catalog. That's a UCAC4, not a Gaia DR2 catalog. So there, you just want to find out where you are to within, you know, sub-arc second accuracy if you can. And I suspect most of I've checked astrometry.net and Bob Denny's plate solve, and one a long time ago from somebody else, I can't remember his name. They all do a reasonably good job. I mean, sometimes the star extraction isn't very good. Sometimes it can't find a plate solution and so forth, but in general, they all work. Okay. Do I mean Hal? Is that Hal 9000? So what I would like to do, so the reason I wrote plate solve doesn't have anything to do with this. What I needed was a plate solver that was all sky. In other words, you didn't know where you were, so you plopped down your telescope. It could be an Altaz or whatever, or it could be a poorly aligned equatorial, and you just want to start it up and be able to find objects without doing anything. And I accomplished that in about 2003, probably. So I used an algorithm that I came up with that I think I described last time even. It uses what I call orcas, which are just ordered quads of stars, and the normalized distances between those stars and so forth. And that was basically because oh yeah, I haven't actually tried that solver, Leon. So I don't know how well it works. I'm sure it works very well too. There are a lot of people have since made, all sky plate solvers and so forth. So I don't think there's anything ultra special right now about plate solve. It does work well. You can take an image from anywhere in the sky, and it will generally solve it if you have enough stars that are extracted in the field. and it's not outrageously small or outrageously big. You know, I mean, it's within the range of normal telescopes. What I'm trying to do here is something totally different than really plate solve, and we shouldn't even call it plate solve. We should call it precision astrometry. So there's a number of sources of inaccuracy, and that inaccuracies will be, some of them will be systematic and some of them will be noise-like or stochastic. Obviously, when you extract the centroid positions of stars on your plate, on your photograph, there'll be a few different noise-like mechanisms that will prevent you from getting a completely accurate centroid position of the star itself. And that can be calculated. Those noise sources can be put into a calculation, and you can figure out just how, what the standard deviation, say, is of the position of the star that you measure if you did it over and over again, right? I mean, assuming you know, you can't ever talk about statistics of a one-time plate solution, but you can talk about, in this case, we can talk about the statistics when you do it over and over again. So those sources of noise are photon shot noise. So photons arrive randomly in a Poisson distribution in time. So you don't get the same number of photons per pixel every time, photoelectrons per pixel. The camera has read noise, and that's a major effect. With CMOS cameras, that's gone down a lot, and it allows us to do a lot more stuff. I don't think we've really even started to explore what we can do with CMOS cameras in astrometry, in astronomy in general. There's sky background noise. So the sky is not infinitely black. There's photons coming in all the time, and they provide various amounts of photoelectrons per pixel. You know, that changes with the photon shot noise. Those are the main ones. Those are the main noise sources that we generally take into consideration. There are others that can be important and tricky, but let's just leave it at that. There are systematic like errors, which can, well, quantum efficiency is just a problem. Well, you don't make an electron for every photon that arrives. So that reduces the signal and in a sense increases the noise, because if you only have a few photoelectrons, then it's going to be a real noisy. Okay. The systematic errors are a bit trickier. The first one is that the catalog isn't perfect, obviously. So suppose you used a different set of stars each time to do this calculation of the position of the target. Well, you know, then if you use a different set of stars each time, there are errors that in each star's position, and those errors would change based on the stars you picked. So that's certainly one source of error. Another major source of error is that the optics of the telescope don't generate a perfect projection, let's say, of the tangent plane of the celestial sphere. So, okay, I didn't need to say all of that junk, but the optics distort the image, right? So if you imagine this perfect projection of the celestial sphere onto a plane in the sky, that is going to be warped by the action of the telescope, by the optical distortion in the image. And that optical distortion will change with time because the collimation of the telescope will change with time. So that can be a significantly difficult problem to overcome. And I don't know, where we're at with that yet. That's going to require a lot of investigation. And that may be the limiting factor for this. I don't know yet. Also, when you point the telescope in different directions, right, you get a different amount of droop in the optics. The gravity vector changes, and so the optics change their collimation not only night by night, but depending on where you point the telescope. So if there's something like loose, and of course, everything is kind of elastic and loose at the scale of a milliarcsecond. So, that's another source of error. I don't even know if you could call it systematic. I don't actually have a good word for it, but whatever it is, systematic, it's not noise-like, but it's not exactly systematic either. It's a flexure problem in the telescope. So, then there's okay, so we covered the catalog systematic errors that can arise if you use different stars. So we need to use different stars. There's variable amount of let's take third order distortion, coma. It's often called coma, but it's a third order distortion. And what it does is it moves the centroid of the image depending on how much coma you have. Yeah, a webcam is nice. So there are these factors involved with telescope optics, with distortion and so forth, which we can all lump together. I'm willing to lump them all together as systematic errors or something. And the job then is to figure out what the best strategy is to reduce both the errors in stochastic processes and errors due to these systematic problems that we face. So one good thing would be to only use the same set of stars every time you're measuring the position. Always make sure that the collimation is accurate, that there's nothing moving around a lot in the telescope. A way to fight that is to always take the images at the same, at the meridian, for instance, so that they're always at the same part of the sky. I didn't cover other effects that we have to worry about. One is atmospheric diffraction. So the atmosphere refraction, the atmosphere refracts light, and it doesn't seem like very much, but it's actually quite a big effect. The difference between, for instance, if you're 30 degrees above the horizon, I used to remember this, but maybe I can't get it right. But it's roughly like this. If you're 30 degrees above the horizon and you look at a star in blue, in other words, let's say even G, let's say G prime, Sloan G prime, and you look at it in Sloan R prime, you're going to see something like a half an arc second difference in its position in the sky. So, I mean, but it's a lot. The atmospheric refraction is pretty huge, right? The benefit that we have is that all of the stars are refracted. We say the same if you're filtered. I mean, you know, suppose you have a narrowband filter and you use that same fairly narrowband filter every time. Well, you'd expect the refraction to not change from image to image. However, that's only if you do it at the same, you know, elevation and the same pressure and the same temperature and all of that. So,
A question.
yeah.
2 years ago, while I was imaging planets, I used an atmospheric distortion corrector.
Yep.
I've sold it. Sadly, now I sold it 3 weeks ago on eBay. I don't do image planets anymore. But what it did, there were 2 prisms in there. So if the light is refracted, then it just refracts it back. Of course, you have to adjust it then throughout the night if a target rises. But couldn't you use something similar?
Yep.
But then somehow motorized to counteract the refraction?
Yeah, we've used they're called ADCs, atmospheric
That's exactly.
refraction correction. And Russ actually, I think, had one. And we, I think, we have a friend at Cal Poly, and he, I think, even tried to motorize it. And I don't know where that went, but ADCs are, yeah. Right.
Dave, I still have that. We never really quite got it working, but ZWO makes a rather nice one. It's not very expensive, but I think could be automated. You know, it would take some design, but I think it would make a nice starting place. But, you know, if we don't do that, then we're going to have to, if that's a significant air source, we may have to always observe it on the meridian, and that's not going to work.
Right. So we got a problem with, we've got a problem there too. So we have to face atmospheric differential refraction, you know, as it's called, AD.
Well, were you saying that if you take it with the same filter, I mean, if you're looking for relative motion, as long as it's sort of close to its, you know, altitude and stuff in the sky, I mean, could you compare images from night to night reliably, or is the problem that we need kind of absolute positions?
You know, I haven't actually worked it out. I mean, I could sit down with a piece of paper and probably get a rough estimate pretty fast, but I've actually never worked it out.
It seems like you could just from the Fitz header know the altitude and do some sort of correction. Is that possible? And the filter, is that reasonable to consider or not?
Well, the atmosphere is a complicated beast. Yeah. Unfortunately, there's something called the lapse rate of the atmosphere. Everybody who flies an airplane knows what the lapse rate is. The lapse rate is how fast it has to do with water vapor in the air and a lot of other things, but it's how fast the temperature changes with altitude.
Okay.
And it's quite important when you fly an aircraft for various reasons, but it's also very important for like making a plate solution, like for many other things, you know, and we never know the lapse rate very accurately because it has a lot to do with how much water vapor there is in the air. And the water vapor also refracts, right? Provides, and if you don't know how much water vapor, then you can't really do a great estimate. Okay.
Yeah.
Yeah, that lapse rate is a really big deal in glider flying.
Mm-hmm.
Yeah, so you want to see what the lift is going to be, and if it isn't kind of within limits, then you don't want to launch the glider.
Yeah. So the lapse rate's important for a lot of reasons, but so I don't think it's modelable in any real sense to the milli-arcsecond level. So we have to kind of live with it. If you use a narrowband filter, then as I said, and narrowband, I mean, we could discuss that all day, but if you use a filter and you have limited the range over which, then every star should do the same thing every time as long as you're more or less pointed in the same direction. So one of the tricks here might be to actually only use stars that are near the meridian and just keep doing that. And, you'll only get a certain amount of data every year. Or you could do that for, what, 4 months or something? I don't know, 4 months out of
Dave,
the year.
wouldn't it be just almost as much or as good as long as you repeat the observation over several months or whatever at the same altitudes each time, so that there isn't any, except for the lapse rate, there isn't any significant variation in the atmospheric distort or the
Refraction.
refraction. Yeah.
I
mean, it seems to me that what you really want to do is, from the standpoint of an observer, is to control all the variables that you have any control of, so that each observation is as near as you can make it identical to the previous one. And that, I think, would minimize some of these consistent or
Of course. I mean, you
Noise
try to
sources.
make it as similar of an observation as you can. The problem is that the lapse rate, changes.
yeah, you can't control that.
The atmospheric transparency also changes, which changes the kind of the color of the star, because, if you have a very non-transparent atmosphere that night, then you get a lot more absorption in the blue than you do in the red. And so, you can't be perfect. I mean, there's a lot of things that are going on here.
I did something along these lines also around 2 years ago. It was a measurement, but not very scientific. I looked at planets at different altitudes in the sky using without the dispersion corrector, just to test how bad it is. What I did is I looked at the red and blue fringing and calculated how much percent is it of the planet.
Yeah,
And
that's a great.
from that, I was able to get a curve. I was able to fit a curve at different
Right.
altitudes. But the error on that, if you would convert the pixels to arc seconds, it was multiple arc seconds. And I guess that's because of that lapse rate. So getting down to milli arc seconds is impossible. So a model here based on my crude testing back then doesn't really work.
Yeah, as I said, there's kind of a half an arc second. If you're at 30 degrees elevation, there's kind of a half an arc second across the visual spectrum. It's a lot. It would make a good paper.
Oh, I would have to find it. It was just a basic graph done in Excel, just out of curiosity.
Yeah, so you can look up atmospheric differential refraction on Google and get lots. You can look up the refraction versus the lots of things, the water vapor content, but as you might imagine, a star going through the atmosphere, it's going to vary from night to night so as Scott said, we try to deal with that by making the conditions as similar as possible, but we'll never get them to be the same. What does that mean? Well, I don't actually know yet. But it's something that has to be sketched out. We have to try to figure out what the randomness would be under various. It's a random process, obviously, right? Because the atmosphere is behaving randomly. And, if that turns out to be 10 milliarc seconds, then, well, that's good news and bad news. It's good news for small telescope work because you can take a lot of images and try over a long period of time and plot the motion, or do trajectory calculations or whatever, and you're going to do as well as anybody else. And then you can try to decide whether an atmospheric dispersion corrector is going to help or hurt. It's not clear to me that it's going to help. It might actually hurt because you're adding yet another variable in the system. So I don't know. So, it's a great thing to somebody to take on as a little subject. What is the effect of the atmosphere on this work? You have to kind of talk about different bandwidths, filter bandwidths. You have to talk about different elevations, night to night changes of the actual refraction of the atmosphere, the dispersion in the atmosphere, and so forth. And it'll even vary across the image. If the image is, a half a degree, there could be a significant gradient in the refraction across the image. It's a great little project. A lot of good physics and mathematics involved.
One of the things I think, Dave, is possible on the atmospheric dispersion and maybe some of the other effects is we may be able to calculate that, rather than having trying to correct it with the counter rotating prisms. We'll know where the telescope's pointing, and we just take some basic atmospheric measurements and crank them in to each one of the stars in the field.
We may be able to calculate it by just looking at the extracted positions of the stars in the images. I don't know. It's a really great field it's a good scientific field to study. There may be lots of papers written about it. Of course. The first thing you do is you send up a weather balloon.
And I'll be going up to Flagstaff shortly, and so I could arrange, and Dave, I can twist your arm to join me in Flagstaff, but we can talk to folks at both NPOI and over at the Naval Observatory, at the 60-inch we visited last time, and so they've been into to these kind of fine corrections on things for quite some time. We may be pushing a little further than they have, but we can certainly take advantage of what they've learned already.
Yeah, so it's kind of a beautiful field for a little bit of scientific investigation. First, of course, you always read whatever papers you can find about these sorts of things. I suspect there isn't that much written because it's not really a very important, except for the guys who do, precision, whatever, they do like to get their catalogs as accurate as possible, but they do a lot of local solutions and things like that. So, I really don't know. Gaia, should be milliarc second precision, their measurements. That's what they claim. Right. So it's all a very interesting field.
Presumably into balloons, aren't you, Calais?
Yeah, it's sort of, I would love to incorporate balloons somehow. I realize it's a stretch.
Calais, I think I was 13 years old, and I had enough money to buy a weather balloon from Edmund Scientific. It was a big, huge rubber balloon, right? Like 8 feet in diameter. The first thing I tried to do is I tried to fill it with hot air using a vacuum cleaner, the exhaust port of a vacuum cleaner. But I couldn't get the air hot enough to make it float. So I looked around and I found that you could make hydrogen by putting, well, I was that kind of a kid. I love to experiment with everything. That you could make hydrogen by putting aluminum foil into a solution of lye, right? Sodium hydroxide. And then you have to dry it. So I learned how to, you can't, it's really wet when and you have to dry the hydrogen and so forth. And I filled the balloon about halfway full, or maybe a third of the way full. And it actually went up. It went up and up and up. And I never, I never did find it. I have no idea, but it was a big, probably a 6 foot, 8 foot diameter weather balloon. But making hydrogen is a little dangerous. I used to fill regular sized balloons and ignite them. They make a nice little flash. I had to give that up. Okay. Weather balloons are fun. I paid I probably paid, $4 or $5 for that balloon. That was a huge amount of money. That would have been 100 lawns I would have had to mow or something. And then I lost it the first time out. Okay, so there are a number of scientific investigations that should be conducted first. One is the effect of atmospheric dispersion, if you like, differential refraction. Another one is the effect of collimation, basically the whole problem of collimation and image distortion. That would be great to get a handle on that. There's the noise floor issue. So these things are all calculatable or modelable on the computer numerically or whatever. They're all really nice investigations. I don't know, maybe they're too advanced for high school students.
I don't know, maybe some, depending on the student. Actually, Pat had a question about PSF that I'm curious about as well in chat. What PSF model would be most appropriate for, or is it kind of one of those things where it depends on the field? Like if it's really crowded, you want to use a PSF where you could use an aperture method for less crowded fields, or what are your thoughts on that?
If the stars are very close together, then they're terrible candidates for you to use in a plate solution. And the PSF has to be measured, The PSF of your particular telescope is going to be different from the PSF of every other telescope in the world. And it will depend also on where you are in the field. Your PSF will be in the corners of the image. You may have a lot of coma or astigmatism or whatever. So the PSF there is going to be dramatically different from the PSF in the center of the image. And so forth. The PSF, trying to separate two stars by subtracting a modeled PSF is very difficult. I think I talked about this the last time. It's enormously difficult, actually. I thought that would be a great thing to do, but it turned out to be not so useful for the various reasons I just listed.
Okay.
Hey, Dave, you mentioned attacking a couple of these topics, like the atmosphere and the distortions through modeling, but for Clay, couldn't you also attack it just through observations and comparisons without getting into the mathematical models of atmospheres and optics and things like that, and make a nice contribution?
You know, Scott, you can always do things empirically. However, there's great value in modeling them first. I'll give you an interesting example of that that occurred just recently. PlaneWave is making this new, very fast Cassegrain telescope, and I discovered that I won't go through the details, but I discovered that some approximations that I used previously no longer apply. And I a little bit of analysis. I did some, analysis on a piece of paper, and it turned out that I found the error more or less immediately. I'd been looking for it for weeks, and I didn't find it. But I actually was quite easy to, once I thought up that mechanism, it was quite easy to find it and then improve it. I mean, you have to. If you don't do the analysis and it's purely empirical, then you don't really learn very much, and you don't know how to apply it to a wide variety of situations, right?
What to do for our itchy kiddos.
Without going into too much detail, which error do you mean?
Without, you mean in the telescope or in the atmosphere?
No, no, you mentioned there was an error in the telescope you couldn't find.
Yeah, it was a testing error, actually.
Oh,
it's not
testing.
in the telescope at all. It's in the way that we test it. And every telescope we put together, we actually we tested under the sky or in a test tunnel that replicates the sky. So we found it, and we don't ship telescopes with this problem because we correct it before we ship it. But it's become a annoyance in making this Delta Rho 350, because when you put everything together, it's supposed to work, right? You put all the optics together, and it doesn't work by a little bit. It's off by enough that it's super annoying to manufacturing. So it was something that we had to correct, and I just got it, more or less yesterday morning, and it, on a piece of paper, it doesn't take very long to actually do the analysis and then to figure out what the problem actually is and compare it to the results we were getting by testing the mirrors. So we could have just assembled telescopes and then corrected the optics by measuring the assembled telescope, taking out one of the pieces, refiguring it, putting it back together. You can do all of that, but that costs money and slows down manufacturing. It's much, much better to figure out what the problem. It was a small mathematical, how do I describe it? Basically, without telling you too much of the secrets, because it's quite important not to give away too much that my colleagues at PlaneWave would, get mad at me about. But the tester itself, the geometry of the tester, had some features to it that required this additional small correction. That's a good way to put it. And we've been using this tester forever, and the problem never came up because we never tested small, fast mirrors. And when you test small, fast, highly corrected, mirrors, the problem arises because of the geometry of the situation. So and it's not hard to do the analysis. And so here, I think for atmospheric refraction, it's not hard to do the analysis. It's a well-known phenomenon in the atmosphere. It just varies with lapse rate and with color and with observing angle and so forth. And you just get all that stuff collected together into a small analysis of how bad it could be. You know, the stars are going to be different colors, and you have to take the color of the stars into account, of the plate salt star, of the reference stars, right? And the reference, the color of your target, and so forth. So, and it's basically grind it out, because there's quite a few variables. So you got to just grind the damn thing out. There's no substitute for just sitting down and kind of working it out.
Dave, since we've blown our 45 minutes, there were two little things that I wanted to
Sure.
bring up just very briefly. And last week, when everybody was moving around, we did have a very small meeting. I think there were three of us, Tom Smith and Rick. And
Yeah, I
myself.
was in the desert. with
Yeah,
two
you were
friends of
having a
mine.
good time, I'm sure.
Yeah,
But I
it was
presented it.
beautiful.
I presented a half a dozen charts, which were my analysis of the NGC 2331. The same date I sent you. Well, actually, it's the one that I sent. 2 data sets. It was the one that you didn't spend any time on. But I wanted to get, and then I mailed out the charts, and I wanted to get people's feedback. And I would like to hear any comments that people have, but specifically, I'd like to hear what you thought about them.
I didn't look at the charts. I'm sorry. Yeah.
That's okay. So anyway, I'd like to at some other occasion get a chance to hear what you thought about them. I could go right to the last chart, and there are basically just 2 points I made. One is that I think what I did was rather primitive and hard, and we need to have. I'm sure you have good ways to do it, but I think we would like to have a better tool than just cut and paste in Excel, which is what I did. There's isn't very thorough, and it isn't very good.
Yeah, there is a lot of work here to do algorithmically, I think. There's various corrections to make, maybe, as Russ pointed out, as everybody pointed out.
Yeah. Well, this was just analysis of how well the 3.66 worked, and how well it what the noise variation was over my sequence. How much the photocenters moved.
Yeah, bring up
And,
the chart if you can. Share your screen and bring up the chart. Let's.
Yeah. Okay. If we've got time, let's do that. Then.
I have one final question after this before the meeting
Sure.
ends.
And we can continue to do this as this is useful. I love to talk about this kind of stuff. So.
Yeah. So here are the charts. And the first chart showed what I did. I collected all those images that you suggested.
Mm-hmm.
And I plate solved. It was 120 subframes. And I plate solved them all with 3.66
Mm-hmm.
Using the UCAC database. And then and of course, generated the 120 files, photometry
Right.
files that go with it.
Uh-huh.
And each one had 224 stars. So it's a lot of data points
Uh-huh.
to look at the statistics on. So what I did was I picked 6 stars and analyzed them over 12 subframes. And I compared the 366 results to the UCAC positions to see how accurate the plate solution was. Then I analyzed the RA and DEC variability over the 13 subframes to see what the random noise was. And then I was interested in, one way to reduce the difficulty of analyzing stuff is to align and combine it first. And so for a dozen subframes, I did that and compared to just averaging, and saw how much the aligned and combined solutions differed from just averaging.
Mm-hmm.
And so there's just 3 charts that kind of quantify that. The first one shows that we got that 366 got really close. The worst error was just slightly over 1/10 of an arc second. So compared to the ARCAC, the UCAC 4 catalog, and that I did that on 2 different images. And then the variability was very good over this 1 hour of observation, generating 120 frames.
Yeah, that's quite decent, right?
Yeah, right. So, but then it's just one snapshot after another, and there's very little changing, except a little bit the altitude of the targets. And then the third one compares aligning and combining to just averaging, aligning, combining, and then doing a plate solution, as compared to just averaging the plate solutions over each one and taking the average. And you can see that the difference is quite small interestingly in RA, but there's a significant difference in declination, or a bigger difference in declination. And that's probably has something to do with the interpolation algorithm, I would think, in the aligning process. And
what program did you use to do the align and combine?
That was PixInsight. And it's
I have no knowledge about.
Yeah, well, there's a whole bunch of different interpolation schemes that you can use, and it's just the standard third order of interpolation or whatever it is.
Could it be
there are a bunch of choices, and they all might result in a different answer, depending on how you do the interpolation.
Yes, but Scott, they can also do variable amounts of stretching and nonlinear. There can be nonlinear aspects to the align and combine too, which we don't know anything about.
Yes, right.
I found.
But I guess my point would be that if you pick one and use it consistently over, observations, say over a long period of time, then those inconsistencies or those systematics are consistent. And so what you're really looking for is change as opposed to absolute numbers or absolute solutions.
Well, so I've done my own kind of align and combines on many of these data sets that we've taken. And if I don't do any nonlinear stretching of the field, then I get slightly worse results in terms of standard error of the mean position. I get slightly worse results than if I did nothing and just used every field non-combined. And that's kind of a surprise to me, because you get more stars, and you get more stars for plate solving, and you'd expect higher signal to noise ratios and all of that, but I haven't got it to work. So, I have some hunches about why that's true, but I can't tell you, I can't 100% tell you why that happens. But
yeah. Okay. And you're right. And it's probably, well. So
I kind of gave up. I spent a month or two doing aligning combines, and, just, I was quite surprised that it didn't help, but it doesn't seem to help.
Huh.
Yeah.
Yeah. Well, that's in terms of the absolute accuracy or repeatability. Which is it? Is it?
Well, it's what I would do is I take what I call an observation, which would be like your 120 images, right? And I wouldn't do anything. I would just process the images, and that's I'd get a result, right? I'd get a curve, an SEMP curve versus okay, Calais. If you want to do this again, do you want to do this? Do you want to continue with this subject?
Well, we could take it offline. I'm not sure we need to.
I think
the session.
Yeah, I would like to actually have something to eat, because I've got some stuff to do this afternoon. So,
Yeah,
and I am kind of a little tired, to tell you the truth.
yeah, well, you
But-
just had a shot.
Yeah, and things still hurt, and you kind of feel like you got like a half a case of the flu or something.
Yeah,
But if you want to do this again next Friday, we can do it too. So my observation, Scott, is that you really have, I guess, the same information, and when you try to do an align and combine, you mess it up a little bit or a lot, depending on how the alignment is done. And I don't think there's any more information to squeeze out of it. That's the problem.
right. The only motivation I had was that I don't have an easy way to look at the statistics of the 120 plate solutions. And I guess that was, and so I tried combining.
Yeah.
And the last, my last chart had two points in yellow. First of all, it would be good. I'm sure you have good ways to do this analysis of significant, sequences of observations. But I would sure like to be able to do better than what I did with just cutting and pasting into Excel. So I would like to have and I think the rest of us would have a better tool for just understanding the statistics of the observations.
Yeah, I have those tools partially created. I'm at a point where I think it's better to talk about it for a bit. This discussion of atmospheric refraction, when I talked to you guys about it, I realized some things that I had not realized before, and that leads me to, more interesting questions about what to do about it and so forth. So I'm certainly not at the point where I can release the tools because they're really half baked, and I can make things a lot worse for everybody if I release tools that aren't verified.
Right.
Validated.
Tom, in the meeting last week, when I made this point, Tom Smith actually volunteered to take a look at the particular data set that I analyzed and see what he could do to come up with a way to better analyze it. So, and he's probably a lot more qualified to do that than I am, certainly. So we may see some. I don't think Tom was on this call, but we may get something from him.
Yeah, he's a real expert at spreadsheet manipulation.
Yeah.
This is quite an interesting scientific investigation that shouldn't be taken lightly. I mean, I don't want us to run around without justifying what we're doing and doing it as well as we can. I mean, a good paper here would be super valuable to the community because there could be something, of value in this work. But if you kind of half bake it and ignore a bunch of stuff, then, you're probably making it worse instead of better.
Yeah.
Yeah.
The other point I made from the charts is that as an observer, what you really need to do is, and I said this earlier, is control the observation variables and make sure that they're as close to exactly the same in each observation.
As well as you can. I don't quite know what to do about variable calibration, telescope alignment stuff, and so forth. That's another area to think about. How do we, what effect does it have? Is it a huge effect? It might be quite a huge effect. I don't know.
Yeah. Well, we may be able to take some measurements and quantify empirically how big the effect is. That's the other very short thing is about a month or so ago, I think there were two fields that were identified as being worth looking at over an extended period of time. I don't know who came up with those fields, but I think I know where they were or are, and I just wanted to ask if those are still fields of interest for us to observe over a period of, say, the next 6 months or so.
Yeah, so I had picked a couple of stars that were fast movers that had
Yeah.
kind of the right, separation and what I thought would be the photocenter motion and so forth. Those stars would be easily accessible starting around the 1st of May. I mean, they're accessible now, except it's 4 o'clock in the morning or something.
Yeah, but that's doable too.
Yeah, everything's doable. So if you like that, if you like this kind of work, then take images of those fields, those two fields of those two targets, and we can work on reductions.
Okay.
Yeah.
Great.
And then Russ had he was working with Ivan. He had a couple of other ideas. So the stars that I picked were, as I said, I think, I recall in my brain that around the 1st of May, they were becoming, not so late in the sky. I mean, late at night, to make them kind of accessible to people.
Yeah, and those were picked, Dave, had a dozen or so that we had we thought they would show significant movement in a few months.
Right.
And we had the plots, so they were known binaries, and we had the plots and the orbital plots, and you picked 2 of those.
Yeah, there was one that had, they were fairly short period, and they moved enough that we thought that over a period of 4 months, we'd be able to actually see some motion.
Yeah.
Scott, if it wasn't too much to observe it, I don't think you have to observe them lots, but get in 2 or 3 more observing sessions before they disappear in the west. That could give us the data and we might have our first photocenter rotation detection. So yeah, keep at it.
Okay. I'll see if I can do that.
Yeah. All right.
That's
well,
really,
I'm gonna sign up for this week.
yeah, that's
and
all I had.
we
Yeah,
can
let's do it again same time next week.
Yeah, unfortunately, I'll be kind of out of reach next week, but I'll see if I can try to get in.
All right. Great. I enjoyed a lot.
Yeah, good. See
And
you,
Russ,
Leanne.
you're in Payson, Arizona. Congratulations.
Oh, yes. It's nice.
You're at the epicenter of astronomy in the West, I think.
Yeah, it's great. I'm delighted.
And you need a camera kit that you can just like a doctor's bag. You just open it up and
Go visit
slap
these
it on
various
whatever
telescopes.
telescope. Yeah.
Yep, I'm going to do that.
Okay. Leon, you had one further question, or were you?
Oh, if you have time, sure.
Yeah.
I was wondering what you meant about the noise floor. You said that would be an interesting field of study. Do you mean only in the camera, or is it related to that SNR spreadsheet you said?
Yeah, so it's related to the SNR. Take every source of noise and model it and see what it does to the calculated centroid position.
Yeah, I would like to do that then in 2 or 3 weeks after more exams, but
yeah. So when you're ready, we can talk about that. I have a fairly decent piece of code that you can take a look at. It sort of works. It works fine. It actually doesn't include every noise source, and it should, but that's a very, very important thing to understand, to write up, to put together a set of PowerPoint charts, and we can go back and reference it from when we need to. I mean, very important work. Yeah. Good. So I'll look forward to working with you on that, and you can probably do a better job at the code than I do anyway. I mean, it should be automated and a lot of interesting things there.
It's Python, right?
My code is in Visual Basic, which is Visual Studio. Visual Studio is C++ plus Visual Basic plus some other tools, and they all compile to the same code, basically.
It'll work.
They all
It's
work.
Same principle each time. So.
Yeah.
Okay.
All right. Good. I enjoyed it a lot. Thanks for being here.
Great.
Dave, I'll be back in California from the middle of May to the middle of June. So thought I might come down and visit you.
Yeah, that would be
And
fun.
maybe even take the train further down and visit Scott and Pat and Grady in San Diego.
And just
Yeah.
keep going.
I love the train, and I'll.
Yeah, be sure and get off in Oceanside. Don't take it past Oceanside. It's falling in the sea.
Oh man. Yeah, that happens, you know. All right. Take care. And Leon, certainly when you're ready, let's talk about, after your exams, let's talk about noise sources in images. It's a good topic.
Sure.
All right. All right, guys, take care.